Hi everyone, my name is Vishal and I have with me here Bhargav. Today we're going to talk about our project which is called Contour-Based Image Detection and Comparison. What is it about? Well, it is to test and analyze various approaches to generate and compare sketches to images. Our primary goal is to develop a generalized model that is capable of generating images given a sketch. Second is to create like a universal model to compare sketches to images. How is this useful? Uh, One, we can use it to generate witness images from sketches to better identify a suspect in a crime. Teachers can use this in a classroom setting to teach better to generate images from rough diagrams for a more visual learning experience. We can generate aerial images from maps. Going over some previous work, first is SketchyGAN, which works on augmented data and uses generative adversarial networks to synthesize images based on sketches for 50 definitive categories. Second is Sketch Your Own GAN, which talks about building easier GANs to help predict multiple possible images given a GAN. Compared to these two, our approach varies or is novel in both the technique front and the dataset front. We build a conditional GAN opposed to a normal GAN. We also compare sketches to images using a Siamese network. We use a more broad data set to train the model. Now let's go over the technique used. Here we've used a flipped data set which contained image to contours. We will be now generating images given the contours. It contains 1,000 outdoor images with 5 hand-drawn sketches for each of this image. Now we'll look at the GAN-based approach. Our idea is to build a conditional adversarial network to synthesize image from the sketch. The approach first split the data into train and test, reprocess the image, then ran it through the generator with downsampling and upsampling based on some set number of layers. Uh, Discriminator is used to classify the real and fake images, and then the loss for the two are calculated independently, merged together, calculated. Then an optimizer is used, and then the model is built. Some key design approaches are that we used a conditional GAN, the batch size layers and network that are set after some experiment, and then we checkpoint the model after each epoch. Here's an output from our model after 5 epochs given resource and time constraints. Here's the input image, here's the ground truth, and here's the predicted image.
As Vishal mentioned earlier, we also attempted a Siamese network approach to comparing images. As shown in the diagram, we are using image pairs to train two sister CNN networks. The two networks have the same architecture, but one takes the sketch as the input, while the other takes the original image as the input. The image pair might represent identical images, which is labeled as a positive pair, or non-identical images, which is labeled as a negative pair. These serve as the labels for the model, and the loss is computed based on the combined inputs and their corresponding label. We use a distance-based loss metric for our model. This is how our model looks along with the image dimensions. The final layer consists of a single unit dense layer with a sigmoid activation function. The single dense unit will predict the probability of the positive class and give us a probability value that will tell us if the image is similar or dissimilar. As seen in the image, our model performed quite well on this data set. The validation accuracy constantly rises before saturating at around 0.84. The precision recall and F1 are also quite good as seen in the table. One of the primary experiments that we wanted to conduct was to see if the model trained on general data consisting of people, objects, faces, and so on will perform well on a purely face-based dataset. Our goal was to create an image comparison pipeline that could be used for any application. As seen in the table, the model does not perform too well on the face dataset compared to our original images. Our GAN model, on the other hand, seems to be doing slightly better. The SSI, which is an image similarity metric that ranges from -1 to +1, is clearly much lower for the face data set than for our original validation set. However, the SSI is still above 0 for the face data set, indicating that the model is able to capture at least some basic features of the faces and give us a similarity score above 0. We set out to build an application that is capable of comparing images through different approaches. This represents our individual pipelines for both of these approaches. The main takeaway from our experiment is that a generalized object comparison model is indeed possible. We would simply require more training data to make the model more robust to variations in the types of sketches and images involved. In the future, we hope to use the output of the GAN, which will have a much richer feature set compared to the grayscale sketch, as the input to the Siamese network. We believe this will lead to much better performance and a more robust pipeline. Combining data from different data sets to train our model will also improve generalizability. Thank you.